Hello. My name is David Souther. I am a software architect and a front-end engineer with Novus Partners. We do a little library in the side at Novus called NVD3, and it uses the D3 graphing library, if this loads, to do some really cool visualizations. And I really don't like D3, that's just a personal opinion. So one of the things that I've wanted to do for a while is figure out what Angular could do to do SVG visualizations. Now, bar charts are easy, line charts are easy. I wanted to do something a little bit more exciting and a little bit more realistic. This is a Hertzsprung-Russell diagram, and it's a piece of astronomical data that is a glorified scatter plot that tells us a lot about the universe around us and a lot about the galaxy that we live in and the physical realm, which I think is really fascinating. It provides not only opportunities for the visualization, but also for some simulations that we can run. So let's spend the next few minutes, probably about 45 minutes, talking about what it looks like to write some Angular code that creates just a gorgeous visualization. Now I'm going to be jumping between two sets of code. The first here in brackets is going to be a very high level, so it's going to be a little bit smaller like this, just so you can kind of get a feel of what the code looks like. And then we're going to dive in here in Sublime to actually look at code specifically. Can we see that well? I know these screens are a little bit washed out.
Maybe invert the color, make it white background.
Absolutely. Thank you. Does anybody have a preferred Sublime presentation view? Also, where is color in Sublime? Okay. Ah, there we go. So let's start out looking at this. What we have here is a bunch of data. This is what you might expect to start with any visualization. We have some JavaScript code, and we have some Angular code down here at the bottom. This is heavily dominated towards the data because data is what's really interesting. And Angular we love because it makes our libraries very small. Now the data itself is 3 points. It's the name of a star. In this case, we're looking at Rigel. And 2 pieces of observational data about a star. If you were to go outside with a telescope and look at Rigel, you'd be able to find out 2 things. The first of these is its magnitude. And the magnitude is how bright a star is compared to other stars. And it's an inverted scale, an inverted exponential scale. So a lower number means that it's higher. So a -1 is about 10 times brighter than a 0 in magnitude. And temperature is a little bit more complicated, but effectively it's the surface temperature of the star in degrees Kelvin. So Rigel is about 12,000 degrees Kelvin. UV Ceti b, probably a binary star system, a lot brighter. Magnitude 16 is going to be at the edge of what a human could see if you go outside. And it's only about 2,670 degrees Kelvin. Much different star. And we'll see some results of that in our Hertzsprung-Russell diagram in a bit. So with that data, we have a function cluster. And we're just creating here a class to maintain a list of these stars. And the local cluster is an extension of cluster itself, which just uses all of this local cluster of data. If you actually go out and look at astronomical databases, the stars above there are about the 85 closest stars to the solar system. And we're in modern browsers, so we can use object create. This isn't 2011 anymore. That manages a list of the star class. The star takes that details, which is an element of that array above, and it manages the temperature, the magnitude, and the name for us. About halfway through, we'll actually start extending these prototypes to do some really interesting things with just this data. That's the data model that we need, and that's going to get us a fair amount of ways through this presentation and this setup. I'm going to jump down past this. We'll come back here in a second, and we're going to look at the Angular itself for a second. If you look at line 220, this is just controller as. So far, it's pretty easy. about what you'd expect, except that line 219, we're working with a G tag. Make this a little bit bigger. We're working with a G tag. This is an SVG equivalent to your div, just a regular DOM wrapper. It's going to contain a bunch of stuff in a tree below it. A little bit too big there. I'm starting to word wrap. And then it has a bunch of circles. And the circle uses ng repeat over cluster.stars, which is that array of stars that we had before. And you notice that it uses ng adder 2 times. Now, SVG is not nearly as forgiving as HTML in looking at garbage and attributes. And as far as the DOM is concerned, Angular interpolation is garbage. The CX attribute in a circle tag can only take a number. It can only take a floating number. So if you couldn't call parse int or parse float on whatever you pass in, unfortunately, open brace is not parsable as an integer. The SVG parser will throw an exception, and your entire application will crash before Angular even has a chance to see the ng app tag on the body, and that will be very, very disappointing. However, the HTML parser is more than happy to let ng adder slip by without doing anything to it. And so this is a little technique that you can use in a lot of places in SVG especially, though you can use this really anywhere, ng-attr-source on an image tag, or href for an a link in your HTML. Basically, all this does is say, wait to put the CX element until I have a value that I can interpolate for the thing on the right. Circle in SVG has its CX and its CY. That just tells us where on the image we're going to put this. X and Y coordinate, 0, 0 is the top right, top left. It's going to fill this with an orange color. It's going to be a radius of 5 pixels. Probably could tell most of that from just looking at the code. The actual interpolation that we do is where things get interesting. We're using scales.x passing star.temperature. Star.temperature, of course, matches to the temperature property of that star that we're iterating over in this ng repeat. Let me scroll up a bit for this scales thing. We're doing another ng controller for a graph scale, which is going to expose this x scale and y scale. And what these are going to do is these are going to return a mathematical function that takes a value, in this case, constrained in the domain 40,000 to 0, and it's going to map it to 0, 500. What this means is that we have a way to take an image that's about 500 by 500 pixels and map that to our actual data model that we're working under. So our stars that we have range from 40,000 Kelvin down to 0 degrees Kelvin. Our Y value, which is our magnitude, ranges from -10 magnitude to 20. And the math to do that is kind of boring. We don't care about that. Let's take a look at this. This is what we get. Let me make that a little bit smaller. We have a 500 by 500 pixel scatter chart with a lot of artifacting on the screens up in front. That's okay. Kind of boring. Let's see if we can make this more interesting. Though, before we move on, you can already see that we have this, this fall off here from the top left down to the very sharp on the bottom right, which corresponds roughly to this chart here. I'll point out a couple of differences in the scales that we're using that lead to different shapes here. But if you showed this to an astronomer, they'd look at that and they'd say, yes, that's a Hertzsprung-Russell diagram of appropriate size. So let's make this more interesting. The first thing I don't like about most D3 examples is that you have to go through a lot of work to go through browser resizing. So I want this to just be kind of part of what I do. So this is the next slide we're going to look through. I took out all the data model. It's in a separate JavaScript file. Sorry, all of the data itself, it's in a separate JavaScript file. We don't need to see that every time. There's a bit more JavaScript here, beef that up a little bit. And we have this massive block here that is a directive that we'll go and look through. So to make this full screen, we have some CSS that keeps this guy the full width and height of the screen. Our cluster, our local cluster, and our star are exactly the same. And now we're expanding our model a little bit so that we can broadcast the window resize event whenever we resize. And then we'll just redigest our scope. We have a filter here that we'll use. And we've got a track scale directive that does a lot of math. But basically, it lets us define an X and a Y scale that will always be correct from our input domain into our Windows output range. And the filter we use here, just to make it a little bit nicer, instead of having to call scales.x pass in star.temperature every time, we're using a more filter approach. I just find that this looks cleaner and looks a little bit more Angular appropriate. Let's go ahead and look at that. Here we go. I full screen this. It immediately comes to the right height. Everything is jumped around. I'm out of full screen and resize the window. And these are all hard-coded absolute pixel values. And it just, on my machine, is smooth as butter. Over the Hangouts, it's a little bit laggy. And it's doing all those calculations on the fly. We'll come back to that in a little bit too. All right, we can make a scatter chart. One of the nice things about science, or one of the amazing things about science, is the lifting feeling that you get when you can really consider the vastness or the magnitude of the universe. At least that's what I get. I don't want this to just be a bunch of little disks. I want to really see if we can make this as aesthetic as possible, very nice to look at. I want it to not only say something valid, but I want it to say something aesthetic. So let's jump back over here. One of the most fascinating things about this Hertzsprung-Russell diagram that I find is that the color of these stars, white in the top left, dark red in the bottom, are in these vertical bands. We've got the white here. You can't see the mouse at all. We've got the white here in the O and B spectral bands. The sun itself is in this yellow cluster here in the middle, G-class spectral stars. This this color is purely defined by the temperature itself. A star is a black body radiator, which means that at certain temperatures it will have certain colors, period. This is a fundamental physical thing about the star, that you will never see a green star because stars can never radiate in the green spectra. That's kind of interesting. It also says that, remember how we have 2 points of data, magnitude and temperature? Well, with that temperature data, we can rescale that. Instead of scaling it to a pixel value, we can scale it to a color value. And that's what we're doing here. Turn off word wrap. I don't like you, word wrap. Lines 85 through 88, we're still in our scale. And we have this new scale called color. Anything that is less than 3,700 is going to get this dark red color. And as we go higher on the temperature scale, for between 7,500 Kelvin and 10,000 Kelvin, we're going to get this very whitish color. And then all the way up to our brightest stars, above 34,000 Kelvin, get blue. And I did not choose these colors. These are actually the colors from the Harvard Center for Astrophysics, which has a very fascinating announcement recently about observation of gravitational waves, which is a topic for a totally separate conversation, but very interesting. So using these, we can now say, let's take this temperature data that we have and pass it through this color scale. Instead of mapping from 0 to 500 pixels, we're going to map from discrete quantized scales into these colors. And again, we use that for the fill property of our circle. So now we have some colors. This is actually starting to look kind of interesting, kind of pretty. Let's take this a little bit farther. Let's see what else we can do. Next up, we're going to change the size. It turns out that just like the magnitude and temperature give us an exact definition of what the color is, again, temperature alone will give us color. If we take the two together and use magnitude as a stand-in for the star's luminosity, that is how much light it puts out, and combine that with the temperature, we know how big it has to be. This actually makes sense if you think about it. We have supergiant stars in the top right. Now remember, on the higher up we go, we have more luminosity, that is, it's putting out more light, but it's also a lower temperature, which means that it has to work harder to put out that much more light. It means that it has to have a larger surface area. It has to be bigger to put out as much light as its luminosity has when it's putting out so much less light from its fusion. Versus these stars over on the top right are very, very hot, which means that every photon they put out is very, very energetic. It has to be much, much smaller in order to have that same luminosity and not completely outshine the bright giants at the same level. So let's go ahead and look at this. This is where it's going to get a little bit more interesting with this star model that I started before. So the first thing, this is where I get less scientific in the favors of aesthetics. Instead of using the same data every time, I'm just going to play with it by about 1/10 of its value so that we get a little bit of randomness in here so that we're not looking at the same image every time. Technically cheating, but we're still using a good enough raw data source that I'm sure you can go and find some stellar cluster somewhere in the galaxy that'll actually match the ones that we're about to come up with. You might have to look to another galaxy, but I'm sure you can find something close enough to this. So the first thing I want to do is I mentioned that luminosity. Now, magnitude is a relative scale compared to what other stars are. It turns out that the magnitude is related as a power function to the luminosity. So the luminosity just follows this law, this expression here. Again, Wikipedia, thank you. About 2/3 of the way through the presentation, Wikipedia fails me, and I'll have to go to an actual stellar nucleophysics textbook that I'll give you a reference to at the end if you want. Size function, same way. If we have the luminosity and we have the temperature, it turns out that the size or the radius of the star is roughly proportional to the square root of the luminosity divided by the temperature to the 4th power. That's not important. The math works because astrophysicists say so, and I'm just here to implement their models. So we scroll down here, and basically we have the same thing. These values are a little bit arbitrary because of the specific parameters of this program, so you couldn't just copy and paste those into another stellar model. But the right two parameters, 3 and 30, tell us the radius in pixels of the smallest to the largest star. And we use that again. Call star.size, pass that through our size scale filter. This is really not very much Angular and just a lot of actually modeling a very interesting physical phenomenon. Let's go ahead and look at this. Here we go. We've got some little white dwarfs down in the bottom middle here, if you can see the mouse, indicating this bottom center quadrant. We've got our main sequence along our nice sloping curve here. We did switch to a log scale so that it's a little bit more correct. We were using a linear scale on the x-axis before. Now we're using a logarithmic scale, which is, if you look down here, how the color, whoops, sorry, that's the color. If you look up here, that's how the spectral class is done. So they really cheat on this one by not using a log scale, but just using some arbitrary thing that they wanted to look good. Art is better than science anyway, right? But we see that we have this very bright star. That's Betelgeuse and probably Arcturus in the top right. And we've got Sirius, his buddies over here, very hot, bright stars. The Pleiades are not close enough that they'd be in this cluster. We've got the sun down over here somewhere in the little yellow group that you can see. This little band of yellow right here. All right. Now we do even less Angular. And in this case, we're doing purely SVG. And I'm not going to bore you with this. You can go through the comments on the GitHub page later. But once we've done this, this is an SVG filter that's going to do graphics manipulation on those disks. Look at this. Now we can start seeing something that actually kind of looks like stars. We've got some glow. We've got some specular diffusion. But you'll notice there's quite a bit of artifacting. There's this big central white blob in the middle of our red star up here. That doesn't look very good. If you look really closely, you can see some boxing happening because the range of the filter isn't large enough. And that's because this filter that I define here, especially in the lighting, has a lot of hard-coded constants. And you can't really just create a filter on the fly in SVG. You've got to do some really weird side work. And basically, if I wanted to create a filter for every star that I had, I'd effectively have to make this an 2n n squared computation to really figure out the right sort of thing here. So I cheat again. And instead of creating, 100 different or 200 different filters to make every star look perfect, I just break them into 3 categories: large, medium, and small. And how do you think I'm going to choose which category to put them in? Oh, right. I have these awesome scales that I built, and so now every problem is a nail for a scale. In this case, if the size of the star that we calculate before, that we map to the radius, is below 1e negative 5, we're going to go small. If it's from 1e minus 5 to 1e minus 4, it goes into medium, and otherwise it goes into large. Again, those numbers are very specific to this particular implementation. Your mileage will vary as you do other awesome pieces of art, which you now know how to do. So we go ahead and pass that through our scales filter. If we look at this and let this render, you can see that looks a lot absolutely terrible on those screens. I promise it looks really, really nice on a nice retina display where you can see the nice bit of glow and the diffusion really matches what you would expect a sphere of a star to look like, a little bit very bright in the very, very center, and then it fades off to the side. So I would encourage you to look at the GitHub project when this is done and play around with this. So let's keep playing around with this. Let's see if there's something else we can do. This is really static. Let me jump over one more step, take another high-level look at the next bit of code we're going to do. Because this is so static, I want to see if I can create a simulation that's keyed to the time step, parameter t, parameterized t. And you see that this time, all the way from, put a cursor in here, about here down to about here becomes our new data model. And this is where it's going to be really cool that we haven't used a raw data table, but we're actually using a smart instance of various things to implement this. Scroll down here. So instead of passing in the 3 parameters that we had before, the name, the temperature, and the magnitude, we're just going to give the star an initial mass, and we're going to fidget with a couple of base parameters. We're going to give it a uniform way to calculate its aging, and every star is going to start somewhere between 0 and 1 epoch time. I put epoch time in quotes because, again, I'm doing a simulation that is very specific to the parameters that I chose and is not actually a nuclear physics simulation because I don't think our browsers can handle that yet, since some of the best Fortran algorithms still can't quite handle those calculations. And now all of our functions, mass takes a parameter t, we calculate the mass. Temperature takes a parameter t, passes that to the mass. Gee, surprise, everything is based off of mass. And again, what I'm doing now is calculating the magnitude and the temperature based off of some very closed form approximations of nuclear stellar nucleosynthesis formulas that, again, I'll give you a reference to at the end because, fascinating things to go and read physics on stars here. And then I can go ahead and say, I can go ahead and subclass my star so that I have, in this case, a hydrogen star. So this star specifically, the temperature and the magnitude functions are going to use assumptions for a star that is primarily fusing hydrogen. Let's take a look at what this guy looks like. Not quite as good as what we had before, but you can still sort of see the average main sequence of stars. Stars that are primarily hydrogen burning are probably going to fall somewhere on this line, at least relative to one another. We're going to have bright blue stars in the top left, dim red stars in the bottom right. It looks like our simulation isn't quite getting to red yet. It just gets down to yellow. All right, this works. Let's extend this a little bit. Let's go on to the next version. In this case, we're going to have, for a cluster, about 3/4 are going to be suns. Those are hydrogen stars. And we're now adding helium stars. Helium stars are heavier and burn helium. And then we have white dwarf stars, which is kind of a separate thing. They do some really weird stuff with a lot of carbon burning and other interesting things. And basically, it's just the same concept. We've got our star, we've got our hydrogen star, that subclasses startup prototype. Helium star does the same thing. It just uses a different approximation for calculating the magnitude and the temperature. The same thing with our white dwarf. Let's look at this. Click the right button. Here we go. We've got our main sequence. We've got a bunch of white dwarfs down at the bottom, and we have our helium-burning giant stars in the top right corner. And if I scroll my mouse wheel, I've also added some animation to this. It took it a little while to do. It doesn't usually go that slow. I'm going to blame Hangouts. And so by scrolling my mouse wheel, I've keyed the mouse wheel scroll to that time parameter that I was passing in to calculate all of those parameters. And so as I scrolled my mouse wheel up, we calculated time forward in our simulation, and Beetlejuice up in the top right there got massive fast. Still looks fine. Don't tell her. She can put some makeup on. And try to scale back out here. If I scroll all the way back to the beginning, I've got these very, very young, very, very bright blue stars. This is before they've had time to swell up a little bit and form planetary disks and become nice yellow stars like we've come to know and love with our sun providing abundant solar energy. So to do that, it's about the same thing. This I find to be a little bit interesting. Use of attribute. Coming back into Angular right now. What we've done, ignore that, those are all the filters. This is kind of fun. I have a directive called scroll that takes some string. And you'll notice that it gets ng initted to be 1. And so all of our scroll directive is going to do, and I think this is really cool. I found this on Stack Overflow. It's going to take those attribute.scroll, whatever was in there, evaluate that against the scope. We're not using expression. That's too heavy here. It's just a simple parameter. And then apply the wheel delta value to that. And so we just have this little thing on our scope that we can just quickly iterate over in and of itself. Not sure how that's going to work for large-scale simulations or for large applications that might have several different data models, possibly even scopes directives below it. But for this sort of thing, it works really fun and very well.
What's wheel delta?
Wheel delta is the numerical value of how much your page has scrolled based off of the wheel click event. So usually if you click one tick on a mouse wheel, that comes out to about 3. That's not a spec, that's just experimentation. In this case, by dividing by 100, I get a really nice animation without having to do any transition in CSS or anything like that. It just kind of works out for my presentation, for my demo here.
Why otherwise it'd be janky?
Yeah, otherwise I would jump by a time step of 3 every time. And in my simulation, going from 1 to 4 is just going to jump you so far along your time scale that doesn't make sense. But from 1 to 1.003 is a very nice, smooth animation. Again, for this simulation, you're going to have to do a lot of tweaking with parameters on your own. So that's most of it. We've got this pretty fun little dealy bob here. One little thing I wanted to take a look at is just think about what performance might be like, but I'm going to hold off on that, mostly just because we're doing Hangouts and that's going to get really weird. See if I can get this. Okay, this looks a little bit better. I will continue on then with performance. The first thing I'm going to do with performance is turn off all of that filtering that I did in SVG. That, as you might imagine, was some fairly heavy graphics manipulation, Gaussian distributions, a lot of work to calculate what every individual star needs to look like that way. So if we back off to just the flat disks, we can get a little bit better feel for what Angular itself is going to do in this situation for running this kind of animation on the fly. It does run very smoothly on my machine. Apologies for the lag in Hangouts. Hopefully we will see timeline here give this a little bit better view. So I'm going to start a recording. We're going to scroll in a little bit. And we can see that we are really breaking our frame budget because of painting. And this is a very different timeline than I was getting before. I should have taken a picture of a timeline before. Earlier this afternoon, I had a great timeline that was coming in at just over 30 frames, just under 30 frames a second. And I was a little bit disappointed about that. I felt like I could have gotten that a bit better if I had taken more time on that. But long story short, I think that this sort of thing will be fine for performance. I did have to make a couple of changes in the simulation code that run the time step a little bit more intelligently that you'll see if you check out the GitHub project. Basically, whereas in the prior version, you can see that we are calling down here, we're passing our time delta, our time parameter to every function every time. In our performance model, we are executing the simulation once with scope.simulate, calls simulate on the cluster once for every mouse wheel tick. And then we don't have to redo all of these computations for dirty checking. We do the simulation once. The dirty checking has raw values, which it can cache immediately and know that we aren't going to have to spend a lot of time going 2 or 3 levels deep on dirty checking. If you want a little bit more information about that, Mishko's Mishko's February Meetup video from Mountain View has some really good information on that. And like many things in Angular, that will only get faster as we move into the future. So this is what you can do. I think it is a very reasonable approach. I gave this demo internally at Novus on Friday, and one of our front engineers goes, when are we replacing D3 with Angular then? I don't know, maybe soon. Thank you. Look at the lights, Jeremy.
All right, so we can do questions now. If you have a question, you can wave over one of us with a microphone so we can get you on YouTube, and we can also try to turn on the lights. Okay, so first question. I saw someone over here.
I was just wondering if you could go into the code of the VG scale that you made, the directive.
I'd rather not. Come talk to me afterwards. It gets a little bit hairy because it was very prototype.
Okay.
It does a lot of assumptions that are not production ready, but the ideas are there. So
Okay.
It'll be on GitHub, and come talk to me afterwards.
I'm curious if you saw, like, was this more of an exercise in how can I do this without D3, or was it more of a, do I see performance increases by being able to drop D3, anything along those lines?
This was very much, I'm curious as to what Angular would do for this problem. At the end, after, again, my internal presentation on Friday, one of the questions that came up was a performance question. Is Angular more performant than D3? In what situations would it be more performant than D3? I don't know. You'll notice that I added this last part of the discussion on the performance to start asking that question. It's certainly a viable approach as an API. Now it's time to dig into it and play around to see what actually happens performance-wise.
Thank you. Um, when you're calculating the magnitude, I noticed that you were using some IFEs on the prototype. Can you explain why you're using IFEs?
What was that?
The immediately invoked function expressions.
Oh, yeah. Basically, it's because I was cheating a lot on how I did this magnitude. We can actually see this right here. What I'm doing is instead of actually calculating the nuclear physics, I go through and map white dwarf stars of 0 to 55 solar masses into the magnitude range of 16 to 10. So if you are a 50 solar mass white dwarf star, your magnitude is going to be about 9.3 or something like that. So by doing that, I can then just pass this pass the mass into that scale. And obviously that scale is per class or per star type. So the immediately invoked function is just to tie that scale only to the function that it's used in.
Okay.
Long answer for a short question, sorry.
Any more questions? We usually have more than that.
Yeah.
I guess not. All right. Well, thank you.
Thank you. Oh,
One more surprise question.
surprise questions.
So you mentioned the scroll wheel.
Yes.
I'm not sure if this would work well on a mobile device, but I guess there is two-finger scrolling. Is there any support for pinch or anything like that?
No idea. I think so. Yeah, no idea. That would definitely be something that a production library would want to take into account for.
I think that Angular might have touch events in its latest version, but I'm not sure. I think they were added, yeah.
I'm kind of surprised that you didn't use Python to do your number crunching rather than Angular, which is JavaScript based.
Again, I cheated. I really did not do real number crunching. I did mapping. I did linear and logarithmic mapping of plausible input domain to a plausible output domain. So there was no actual number crunching. The Fortran joke was very serious. I can't do that level of number crunching like you'd expect in here. So I cheated and made something that looked what I think looks pretty reasonable and good, while taking accurate assumptions of the physical model that we understand and creating something hopefully artistic.
All right. Well, thank you.
Thank you.
Oh, one more question.
Oh.
So, the implementation of SVG, especially with filters, I think is slightly different. What would you say is a good idea for a library that does graphing as far as compatibility? Because that's what D3 allows you to abstract from.
So I'm trying to, oh, there you are. D3 is, this is from my experience managing the NVD3 project in the last couple of months. D3 is very good for quick and dirty visualizations. D3 has a lot of fantastic math libraries. In fact, in a couple of slides that I didn't end up using, I calculate some cubic interpolations of path functions that you would use in a line chart. I gave up. I just copied the D3 math libraries in, called the D3 math libraries to do the math work, the math visualization part of it, and just passed those off to the Angular filters that that you saw me define. We also have a path filter that can take an array of data and create an SVG path line chart through the data here. Actually, I can show you that right now. That is my index page. I want to go to this page. So this is just a simple line. You can't see that very well. But then if we go to this slide, it's the same line, but using a different SVG path function, path attribute, and it gets nice and smooth. I think it looks a lot better in Angular because you have that DOM manipulation right there. You're not going through the weird selection approach that D3 takes. ng-repeat makes more sense than d3.select to me. That's the long and short.
All right. Any more last questions?
Any super secret questions out there?
Feel free to talk to me afterwards.
All right. Thank you so much for speaking.
Lightning demo.